Let's test the capabilities of LPSolve versus a very common method of linear programming, the Excel solver solution. To begin, let's look at the LPsolving gradient matrix for a typical formulation of a calf starter. In this formula, we have 15 ingredients, including soy hulls, wheat midds, beet pulp, corn gluten feed, and a number of other ingredients. The columns are organized by price or cost, and then the minimum and maximums for each ingredient. We see here wheat midds is set to have a maximum of 20%. The following columns are the nutrients: dry matter, protein, fat, ash, starch, the minerals, Me, MP, etc. You'll notice that the columns in blue are the ones that contain a minimum or maximum. The columns in gray don't contain either a minimum or a maximum. For the sake of this comparison, we're only going to look at the columns that contain a min or a max. At the bottom of the grid, we see two rows, minimum and maximum. This is where the min or max of each nutrient is included. These are dry matter, protein, fat, ash, starch, calcium, phosphorus, sodium, and magnesium. Notice that we don't have any maximum set in this formula. Now let's take a look at Excel. I created a spreadsheet that is set up exactly like the grid in LPSolve. I copied all of the cells from LPSolve into the spreadsheet and organized them in the same way. We have the columns ingredient, price, min, max, etc. I added one column called unit, and I'll explain why in just a moment. Then we have the nutrients dry matter, protein, fat, ash, starch, calcium, phosphorus, sodium, and magnesium. For the moment, all of the other columns that are available within LPSolve are not included in the spreadsheet because they're not involved in the calculation of the least cost formula, since they don't have a min or max. I've added three new columns called percent, lower prices, and upper prices. These are presented by LPSolve after we find a feasible solution, so we need to include them here. Below the minimum and maximum rows, I've also included rows that are printed by LPSolve when we find a feasible solution. These are the actual nutrient composition, as well as the total price, and then the shadow prices for the minimums and maximums. And we'll look at these in more detail in a few moments. The unit column is required by any linear program to perform the actual minimization or maximization. Each of these units has to be equal to 1, and then the total needs to be equal to 100. This forces the linear program to actually do the calculations and calculate the percentages provided here in column Q. All of the data above the actual line are included as simple numbers. There are no calculations in any column here, including the percentage column. This will be calculated by the LP algorithm to calculate the total cost and the actual inclusion rates. The actual line is where the calculations occur. Let's look at the minimum and maximum columns first. We have some entries here. So for example, wheat middlings has a maximum of 20%. I'll name this cell max mids so that when we begin the calculations in the solver algorithm, it's a little easier to understand. I'll do the same for fat, molasses, canola, and the premix numbers min and maximum. If I were to generalize the solver spreadsheet, I would probably name these a bit differently. But for the sake of this simple demonstration, I'll just include the names as they are fixed for the rows. The actual price cell is the value that's going to be minimized, and I've named this cell total cost. We multiply the percentages in column Q by the prices in column D to calculate total cost. We do this using the formula sum product that allows Excel to do this calculation by row for both columns. It's an easy and quick way to do this calculation. For each of the columns within the actual row, I do a similar calculation. The sum product of the column for each of the ingredients multiplied by the percentage. This will then calculate the actual percentage for each of the nutrients, dry matter, protein, fat, etc. This is a critical calculation because this will actually do the calculations based on the formula, which will set the minimums and maximums for each nutrient. So you can see here that I've set the sum product for each of the cells within row 21 to match the calculations for the percentage of nutrients based on the percent inclusion of the ingredients. For the nutrient minimums in row 19, I've named each of the columns within the row by the nutrient. So I have min dry matter, min protein, min fat, min ash, etc. Again, this is just a way of making the calculations within the solver engine a little easier to understand. Cell G1 is the total formula and needs to be equal to 100 for the actual list in row 21. I'm also naming each cell to make it a little easier to understand. For example, cell H1 would be the actual dry matter. Actual protein is I21, etc. This will allow us to understand more easily the calculations within the solver engine. Now let's take a look at the solver calculations. Now, solver is not always included within a basic Excel installation. You may need to install solver. There are a number of resources available online that can help you with that method of installation. If you don't have solver installed, go to one of these resources and install the package. Now that you've installed solver, we'll go to the Data tab and click on the Solver tab to bring up the solver parameter window. This allows us to enter the inputs required to run the linear program. We'll first set the objective as total cost, that is cell D21. This is the value we want to minimize. Remember, total cost is calculated as the sum product of the percentages by the cost of each of the ingredients. The values we're going to change include the column percents. I've named this for each of the percentages for all of the ingredients within the formula. This is column Q. So we'll change the percentages in order to minimize the total cost. Next, we include the constraints. That is, the requirements we've indicated for both ingredients and nutrients. I'm going to begin by addressing the ingredient minimums and maximums. Now remember, I named each of the columns or cells to make it a little easier for us to understand. The first constraint would be the actual MIDS percentage, which needs to be less than or equal to the maximum MIDS percentage. We repeat this for all of the ingredient maximums. Remember, in order to generalize the solver spreadsheet, I would need to make these values more general to include minimums as well. Now we'll set the nutrient minimums and maximums. We add each constraint in turn. The actual protein needs to be greater than or equal to the minimum protein. The actual dry matter needs to be greater than or equal to the minimum dry matter, and so forth. One constraint that's critical to make the LP run is the total calculation. That is, the percentage by the units. The units being ones that need to equal to 100. This is the constraint that actually drives the formulation. Once I've included all the constraints and checked them carefully, I'm ready to run the solver engine. I'll check the box here that says to make the unconstrained variables non-negative, which makes sure that any inclusions would be greater than 0 or would be equal to 0. Next, we select the solving method. We're going to use the simplex LP method. That's similar to the LPSolve 55 algorithm that's used within the LPSolve software. Once we set our parameters, we're ready to do the actual least cost formulation. Solver will do its calculations, and if it finds a feasible solution, it will return the results, as is shown here in the solver report. The solver results reports that solver found the solution. All constraints and optimality conditions are satisfied. So we're given the option of keeping the original solver solution or returning to the original values. We also have the option of selecting any one of 3 reports. For our purposes, we're going to select the sensitivity report because that gives us the information about the solution that we've generated. So I'll click on Reports, Sensitivity Analysis, and then click OK. We see that solver returns an optimal solution with a price of $140.82. The formula contains 36.5% soy hulls, 20% wheat midds, 35.06% barley, etc. All of the ingredients are included at less than or equal to the maximums that we've set. In this case, the maximum percent wheat midds is 20%, and the solution contains 20% wheat midds. The vitamin mineral premix is set at a fixed amount of 0.25% with the minimum and maximums that are shown here. The nutrient specifications have all been met. The minimum is 17% protein, 3% fat, etc. Some of the requirements are binding and others are not. For example, the ash with a 4% minimum is actually 7.34%, which is greater than the minimum, but since we've set no maximum, this is allowed. Magnesium has a minimum percentage of 0.2, but we've included 0.28% within the formula. Now that we've set up the formula within Excel, let's run the same scenario with LPSolve. The conditions are all set similar to that in the Excel spreadsheet. I'm ready to click the Run button, which will ask LPSolve to do its LP linear optimization. LPSolve also finds a feasible solution with a cost of $140.82, exactly the same as that of Solver. The percentages are also the same: 30.65% soy hulls, 20% wheat midds, etc. The nutrients are also identical: 17% protein, 3% fat, 7.34% ash, etc. You'll notice the LPSolve output provides some additional information. The lower prices and upper price columns are shown to the right, and under the actual column, we see we have some additional shadow price information. Now, Excel also provides us with this information, but it's included here in the sensitivity report. Excel provides us with the sensitivity report in a new worksheet that's called Sensitivity Report 1. The upper values here are the value variable cells, which provide us with information about the prices of each ingredient. These values correspond to the lower and upper prices presented in the LPSolve columns. The calculations are slightly different, but the actual numbers, when calculated, are identical. Below we see the constraints. These values correlate to the numbers within the LPSolve shadow prices, and in this case the shadow prices minimum and upper and lower limits are calculated using the same numbers as presented by Excel. To generate the same values, we need to do some calculations from Excel, but essentially once the numbers are calculated, they're identical. To do the calculations and to understand the implications really requires some knowledge of linear programming and how sensitivity reports can be calculated and interpreted. This is beyond the scope of this demonstration, but essentially the numbers that are presented in the sensitivity report, when calculated, are identical to those that are presented in the LPSolve results. Let's wrap up by making a few changes to the requirements and see if the results are still the same. I'll change the maximum midds to 25%, increase the minimum protein to 18%, set a 7% maximum ash, and change the price of beet pulp from $145 a ton to $130 per ton. Note that when I make these changes within LPSolve, each of the changes is highlighted. It makes it a little easier for me to remember what changes I've made within a formula. I'll next do the same changes within Excel. Now remember, when I set up the Excel spreadsheet, I didn't generalize, so in order to include maximum ash, I need to add another constraint to the solver set of constraints. So I'll name the constraint and also the percent and add the maximum constraint to the solver matrix. I'll delete the Sensitivity Report 1 worksheet so that when Solver completes its evaluation, the sensitivity report won't be duplicated. So now that we're ready, I'll click on Solver and ask Solver to run its evaluation, and we'll look at the results. Here we see the total costs and percentages. We see the total costs between the two methods of calculation are still identical, as are the percentages included in the formula, as well as the nutrient specifications. So you can see that within the parameters of a typical ration formulation system, Solver within Excel and LPSolve provide us with the same set of calculations and the same outputs.